Electric cars, trains, trams and boats already exist. That logically leads to the question, why are we not seeing large electric aircraft? And will we see them anytime soon? Why do we have electric cars and trains, but few electric planes? The main reason is that it's much simpler to radically modify a car or train, even if they look very similar to traditional fossil fuel vehicles on the outside. Land vehicles can easily cope with the extra mass from electricity storage or electrical propulsion systems, but aircraft are much more sensitive. For instance, increasing the mass of a car by 35% leads to an increase in energy use of 13 to 20%. But for a plane, energy use is directly proportional to mass. Increasing its mass by 35% means it needs 35% more energy, all other things being equal. But that is only part of the story. Aircraft also travel much further than ground vehicles, which means a flight requires far more energy than an average road trip. Aircraft must store on board all the energy needed to move its mass for each flight, unlike a train connected to an electrical grid. Using a heavy energy source thus means more energy is needed for a flight, which leads to extra mass, and so on and on. For an aircraft, mass is crucial, which is why airlines fastidiously weigh luggage. Electric planes need batteries with enough energy per kilogram of battery, or the mass penalty means they simply can't fly long distances. Short-range planes. Despite this, electric aircraft are on the horizon, but you won't be seeing electric 747s anytime soon. Today's best available lithium-ion battery packs provide around 200 watt-hours, Wh, per kilogram, about 60 times less than current aircraft fuel. This type of battery can power small electric air taxis with up to 4 passengers over a distance of around 100 kilometers. For longer trips, more energy-dense cells are needed. Short-range electric commuter aircraft that carry up to 30 people for less than 800 kilometers, for instance, specifically require between 750 and 2000 watt-hours/kg, which is some 6 to 17% of kerosene-based jet fuel's energy content. Even larger aircraft require increasingly lighter batteries. For example, a plane carrying 140 passengers for 1,500 kilometers consumes about 30 kilograms of kerosene per passenger. With current battery technology, almost 1,000 kilograms of batteries is needed per passenger. To make regional commuter aircraft fully electric requires a 4 to 10-fold reduction in battery weight. The long-term historical rate of improvement in battery energy has been around 3 to 4% per year, doubling roughly every 2 decades. Based on a continuation of this historical trend, the 4-fold improvement needed for a fully electric commuter aircraft could potentially be reached around mid-century. While this may seem an incredibly long wait, this is consistent with the timescale of change in the aviation industry for both the infrastructure and aircraft design life cycles. A new aircraft takes around 5–10 years to design, and will then remain in service for 2 to 3 decades. Some aircraft are still flying 50 years after their first flight. Here come the hybrids. Does this mean long-distance flying will always rely on fossil fuels? Not necessarily. While fully electric large aircraft require a major, yet-to-be-invented shift in energy storage, there are other ways to reduce the environmental impact of flying. Hybrid electric aircraft combine fuels with electric propulsion. This class of aircraft includes design without batteries, where the electric propulsion system serves to improve the thrust efficiency, reducing the amount of fuel needed. Hybrid electric aircraft with batteries are also in development, where the batteries may provide extra power in specific circumstances. Batteries can then, for instance, provide clean takeoff and landing to reduce emissions near airports. Electric planes are also not the only way to reduce the direct carbon footprint of flying. Alternative fuels, such as biofuels and hydrogen, are also being investigated. Biofuels, which are fuels derived from plants or algae, were first used on a commercial flight in 2008 and several airlines have performed trials with them. While not widely adopted, Significant research is currently investigating sustainable biofuels that do not impact freshwater sources or food production. While biofuels do still produce CO2, they don't require significant changes to existing aircraft or airport infrastructure. Hydrogen, on the other hand, requires a complete redesign of the fueling infrastructure of the airport and also has a significant impact on the design of the aircraft itself. While hydrogen is very light, hydrogen contains 3 times more energy per kilogram than kerosene. Its density is very low, even when stored as a liquid at -250 degrees Celsius. This means that fuel can no longer be stored in the wing but needs to be moved to relatively heavy and bulky tanks inside the fuselage. Despite these drawbacks, hydrogen-fueled long-distance flights can consume up to 12% less energy than kerosene.